Welcome to Innova World.
Hello, today's lecture is about thermodynamic cycle for turbojet engine. In this tutorial, you can get a tricks how you can easily memorize the efficiency formula for various components in the turbojet engine. Turbojet engine can be classified in 5 sections: air inlet, compressor, combustion chamber, turbine, and exhaust or nozzle. In the exit of the combustion chamber will be having the highest peak of the temperature, and in case of the compressor there will be the pressure will be the highest peak compared to the other one. Okay, so this is our TS diagram of a turbojet engine. So here in the TS, what is T? T stands for temperature. S stands for entropy. Okay. Now here we know in turbojet engine, it has 5 main components. What are the components? Diffuser, compressor, combustion chamber, turbine, nozzle. So what the diffuser does? Diffuser, it sucks the inlet air. So we can see here, as it sucks the starting point, gradually what happens, this 0 1 and this 0 1 dash. So what's the difference between 0 1 and 0 1 dash? The 0 1 dash is the ideal condition, or rather we can say an isentropic condition. 0 1 dash is an isentropic condition or ideal condition. Both stand with the letter I. This is a way you can remember. And the thick line, you can see the thick line going from A to 0 1 is the actual condition. 0 1 is an actual condition, or rather you can say as A. Right? Now what happens here? So in actually what you see, there is some increase in temperature with respect to the entropy. But whereas in isentropic condition, what happens? That isentropic condition, that is S is equals to constant. S is constant and the temperature gradually increases. Okay. After it enters in the compressor, this is a 0 1 is the entrance of a compressor. Here what happens? The compressor, the pressure increases. The pressure increases. So 0 1 to 0 2, what happens here? Again by as the little bit of pressurized air enter in the diffuser, will enter into the compression now. So when it's entering, what happens? The compressor, it increase the pressure. So here also it will increase the temperature as with respect to the entropy. So what happened? Here also we have two components, that is 0 2 and 0 dash, 0 2 dash. So here also 0 1 to 0 2, what we have? Here also we have a straight line with a means of dotted line. Can see by means of dotted line. So what it happens in the dotted line? This is also an isentropic condition where the S is equals to constant. But actual condition, what happens? 0 1 to 0 2, there is some inclination, curvature. That means there is a increase in temperature with respect to the entropy. Now what happens? Now after it leaves the pressurized air leaves and enters where? Combustion chamber. This is the point 2 is this is a entrance point of an combustion chamber. So in combustion chamber, what happens? There is a combination of the air and fuel mixture. Combination of air and fuel mixture where the heat is added into the system. Where the heat is added into the system. So if in the problem, in any other problems, they will give you the maximum temperature. So what do you mean by maximum temperature will occur where? So maximum temperature will occur at the exit of an combustion chamber. Where? At the exit of an combustion chamber. And or rather we can call as an inlet of an turbine, inlet of a turbine, or the exit of a combustion chamber. So after that, so this is a point we have our T max, or we can rather call T03, where we have the maximum temperature. Now after that, this air and gas, the high hot gas, where it happens, what happens, it's come out from the turbine. So as we comes out from the turbine, we can see that there is an increase, automatically there is always an increase in entropy, but when it leaves from here, there is a decrease in temperature. What happens in turbine? There is an increase in entropy actually, but there is a decrease in temperature. The temperature is gradually decreasing. And here you see, here also we have a dotted line, that is this process, that is 04, is an isentropic process where ideally what happens, S is constant. Similar process happens that it comes out from the nozzle. So what is it? We know the function of a nozzle. What happens to increase the velocity? So what happens here again, as we increase the velocity, what happened? The temperature decreases, pressure also decreases to increase the velocity, because the pressure and the velocity are inversely proportional to each other. Now here also the same thing. In ideal case or isentropic case, always this dotted line will be a parallel to this temperature line. Parallel to the temperature line. So this is a basic fundamental diagram you should remember. And one more point here, from the diffuser to that point, what happens here? This is an inlet velocity. Guess that Ci is an inlet velocity. Okay, so the Ci is the inlet velocity, the difference of A and 01. Difference of what? This is a point drawn horizontal line, from here drawn horizontal line. Difference of this two can be expressed by means of Ci square by 2Cp. 2 square by Cp. That is a difference between. So rather we can write, that is T01 minus Ta equals to Ci square by 2Cp. So in case when there is a requirement, you can apply this value. T01 minus Ta, the value is Ci square by 2Cp. Similarly, what happens in nozzle? The exit gas comes out. In case we name as a exit velocity. Well, how we denote it? C suffix E. So here also same thing. The difference between the T04 minus T5. These are the actual value, not the isentropic value. We are not calculating any isentropic value. We are only calculating the actual value. That is T04 minus T5. The difference gives that Ce square by 2Cp. Efficiency of an diffuser, compressor, turbine and nozzle. How they are interrelated using their isentropic and actual relation. Here in exam point of view, you can easily remember by remembering this technique. Now we are talking about this main efficiency, that is a ram efficiency or diffuser efficiency, can be denoted by the letter eta D. Compressor efficiency eta C. Turbine efficiency eta T, and nozzle efficiency eta N. Eta N. Okay. So now how you can remember this efficiency? Eta D is nothing but the ideal by actual. Here eta C is also ideal by actual. Eta T is actual by ideal. Eta N is actual by ideal. Now what does it mean ideal? I by A. I by A is ideal by actual. Right? So what is meant by ideal? Nothing but the isentropic relation. Okay. Now you see the diffuser. Now we focus about the diffuser. Now see the diffuser correctly. What we have, that is point A and 0, 1. So A is a, what is the A point? A and 0, 1 is the actual point, and A and 0, 1 is the ideal point or isentropic point. Now who is higher in the temperature? 0, 1 is in the higher. So what we will write is ideal 0 T01 dash T01 dash minus TA divided by T01 minus TA, because we know 01 minus TA, T01 minus TA is an ideal condition. So this is D. Okay. Now let me take TA common outside. Now let me take TA common outside. What we will get, T01 dash by TA minus 1. Here T01 minus TA. Let it be like that. Now we know by isentropic relation, that is T01 prime by TA equals to P01 by PA gamma minus 1 by gamma. What is gamma? Gamma is an adiabatic constant. Gamma is an adiabatic constant. So now we are going to substitute this value in the above equation. So eta D. So eta D equals to TA P01 by PA gamma minus 1 by gamma minus of 1 divided by TA. Let me take it common. T01 by TA minus 1. Let me cancel this TA. Okay. Now how we can write this one? Okay. So also we know that you will be knowing that T01 by TA is equals to 1 plus gamma minus 1 by 2 m square. Right? Now again we are going to substitute this value in this equation. Substitute this value in this equation. Let's see what happens. Eta D equals to P01 by PA gamma minus 1 by gamma minus 1 by, in place of this we are going to substitute this value. So 1 plus gamma minus 1 by 2 m square minus 1. This minus 1 and this plus 1 will get cancelled. Eta D equals to P01 by PA gamma minus 1 by gamma minus 1 gamma minus 1 by 2 m square. In some of the books you can find they have directly given this formula to you. So you don't need to work so hard to remember this. Remember a few of these small formulas, this one and this one, and you will get this formula right on your hand. So you remember this technique what I said, that is in this left hand side, what you have left hand side, all the formulas you are having, that ideal by actual. See these are the left hand side, that is all are I by A. So ideal you know what is the value, and actual you know. So both the side we have ideal by actual, ideal by actual. And the right hand side you see, that is turbine and nozzle, both we have an actual by ideal, actual by ideal. Okay. So remember that, and just like this diffuser equation, you can find this expression in a very easy way. Now we are going to find the compressor efficiency. So recall the figure, that is Ts, it's going like this from the point 01 to 02, and this is a point is 02 dash. Okay, so what is the fundamental formula? I said eta c. Eta c is what? That is ideal by actual. So what is ideal? Isentropic temperature divided by actual temperature difference. Now let's write it down. What is isentropic? This is 0, 1 to 02 dash. But who is in higher temperature? Obviously 02 dash. So write 0 T02 dash minus T01. Next T02 minus T01. Because this is our actual line, this is our ideal line or isentropic line. Now similar way, what we are going to do, we are going to take the T01 common. T02 dash by T01 minus 1 divided by, let it be like that, no need to change, is equal to eta c. Now this is an compressor, so we know that there will be a compressor ratio. What is the compressor ratio? P02 by P01. So as per isentropic relation, again in isentropic relation, that is T02 dash by T01 is equals to P02 by P01, the gamma minus 1 by gamma, or rather we can say R C gamma minus 1 by gamma. Now this value we are gonna substitute over there. Eta C equals to T01 RC gamma minus 1 by gamma minus 1 by T02 minus T01. Is that clear? So usually when you solve any problem, you need to find the T02 minus T01. So how we can find T01 by eta C RC gamma minus 1 by gamma minus 1. In some of the textbook you can see this formula has been given to you, so no need to worry about it. Remember the basic formula. This is a basic formula, and you know how the procedures. What is a fundamental concept? That is, in compressor you will be having an P02 by P01, that is a compression ratio. There is a compression ratio. Then from isentropic relation, write this. Then what do you mean by P02 by P01? That is RC. Write there, substitute there, and what is the unknown value? From this value, just exchange that, and you will get the expression. Now we are going to find the turbine efficiency. Now we know the turbine efficiency is a point between the 03 and the 04. The thick line is the actual line and the dotted line is the ideal line. So as per formula, what we know, eta T is an actual by ideal or isentropic, right? So here also we are going to write a relation between the T and the T between these 2 points. So actual T03, because the point 3 is in higher compared to the point 4. So T03 minus T04 by T03 minus T04 dash. So eta T. Okay. Now similarly here T03 minus T04 divided by T03, let's take it common. It is 1 minus T04 dash by T03. So we know that T04 dash by T03 equals to P04 by P03 gamma minus 1 by gamma. Gamma minus 1 by gamma. So we are gonna apply it over here. We can write, then overall we can write like this: T03 minus T04 equals to eta T03 in the bracket 1 minus P04 by P03 gamma minus 1 by gamma. This is one of the expression to find this relation. Now we are going to see a nozzle efficiency, that is eta n. So this is a TS diagram for nozzle. Nozzle, what is the purpose of nozzle? To increase the velocity. So increase the velocity, pressure will decrease and the temperature will also decrease, because pressure and the velocity are inversely proportional to each other. Now what we have studied, what is nozzle efficiency? That is actual by ideal or isentropic form. So now we are going to write a temperature in between the actual and the ideal. So who is having the highest temperature? High, that is 4 compared to the 5. So first we'll write T04 minus T5 divided by T04 minus T5 dash. Right? Okay. Now what we are going to do? Now same as the other one, we are going to take the T04 outside. We are going to take the T04 outside. So 1 minus T5 dash by T04. Okay. Now what is T5 by T04? It is P5 by P04 gamma minus 1 by gamma. Now this value we are going to substitute over here. Okay, eta n T04 by T5 by T04 is 1 minus P5 by P04 by gamma minus 1 by gamma, close the bracket. Okay. Now using this relation, P04 minus P05 equals to eta n into T04 1 minus P5 P04 gamma minus 1 by gamma. This is the expression for the nozzle. As per the given data and the given requirements, we can write. So we also know another thing, that is T04 minus T05. That is this distance between these two, what we have said in the first one, that is it is an CE square by 2 Cp. 2 Cp. What is Cp? Is a specific heat at constant pressure. Specific heat at constant pressure, we usually consider 1.005 kilojoule per kg Kelvin. Kilojoule per kg Kelvin. So we, instead of this, that is C04 by minus C5, we can also write CE square by 2 Cp equals to eta n T04 1 minus P5 by P04 gamma minus 1 by gamma. This can be another final expression for the nozzle efficiency.
Lecture prepared by Ms.Aishwarya, Department of Aeronautical Engineering. Thank you for watching.